Next, we can talk about the Newton's method. So we were talking about how to find the root of a nonlinear equation. And we have seen the bisection algorithm so far. So the second alternative we will see is the Newton's method, or the so-called Newton-Raphson algorithm. And let's talk about how this can be derived. So first of all, we need to consider the Taylor expansion of a function f of x. Okay, suppose that we have this f of x. So if you think about the Taylor expansion, we know. So we can write f of x as a linear approximation, and we can evaluate our function at a point x0. And then remember that we take the derivative and we need to multiply with this term. And of course you have the higher order terms, right? This 0 squared divided by 2 factorial and so on. So in this type of expansion, so basically here we want to have, instead of x, so instead of x we have actually x plus h, and instead of this x0 we will consider x. So if we rewrite things in the first order Taylor expansion, you can see that we will end up with this f of x, right, for this guy. And then this x minus x0, this will be just h. And then again, this x0, you just substitute with x. And you can see that this is the first order term. And all the remaining terms, you have this in the remainder. And the order for the remainder can be represented with this big OH square. Okay? So we have this side purely coming from this first order approximation that we can use for this f of x. So now notice that we are trying to find the root of this function. So if it is a root, I mean if we denote the root of this function with this r, it satisfies this equality, right? Because that's the meaning of being the root of this nonlinear function f of x. So in that case, we are looking for this value of r, and the reason we write this now as x plus h is because we want to find this h such that we get, we can find the root of this function. And if we do this iteratively, in other words, we will find this h in every iteration in our algorithm so that we keep getting closer and closer to the root of this problem. Okay, so this is what it means for being the root of this function. And here you can see that we can set this h equals to r minus x. So here the critical thing is, now if the left hand side of this equality is going to be 0 because it's the root of this function, then what should be the value for this h, right? So what should be the value for this h? So once we get this right hand side, you can solve this equation. So you can solve this equation with respect to h, and that's going to give us the basically formulation. So here is the solution. Okay, it's not difficult. You can just use some simple algebra to get this h value. And basically this gives us, if we calculate this h, we can add to our initial x. So that will give us a closer value to the real root of the problem. Okay, so you can see that if x is an approximation to r, then this is going to be actually, this is x plus h, right? So this should be a better approximation to the root of this problem. So this is the main idea in the Newton's algorithm for the root finding problems. And also we can see a geometric interpretation of what's going on in this algorithm. So suppose you have this f of x function here, and basically we need to start with some initial guess. Okay, so you can see that suppose we start with this x0. So what this algorithm does is basically we have this tangent line. You can see we have the tangent line. So we are going to the image of this point on this f of x, and we move along this tangent line until we cut this x-axis. So this gives us the next x value, and then we repeat the same procedure. So we again go back to our f of x. We are evaluating our function at this x1, and then using the tangent line, to get closer to the real root of this problem. Or alternatively, you might be starting on the other side of the real root. If this is your x0 that you start the initial algorithm, then you will go to this f of x value, and then it will take you by the tangent line to, again, right hand side of the equation f of x, and then again you will repeat these with a few more tangent lines. You can see that we are really getting close to the real root of this function in just a few iterations, actually. So this is, as you might see from the geometric interpretation, it's actually a faster algorithm compared to the bisection method. However, notice that in order to calculate these h values, additional to being able to evaluate our f of x, we also need to be able to evaluate the derivative f of x, right? Derivative of the function at the same x value. So it has one more requirement, because it is utilizing also the derivative of f of x. However, at the end, we get a faster convergence compared to the bisection algorithm. So if you look at here, we see a sample Matlab code. You can use this for reference as a pseudo code for your own functions. Basically, we need to input a few parameters, such as what's the initial starting value to start the algorithm, x0, what's the maximum number of iterations that you want to run your iterations, and you need to input what are the tolerance levels to define your stopping criteria in this if statement here. So you can see that we have two types of conditions. Basically, if our x values are not changing much from one iteration to the other one, I mean, if the new value of this x is already very close within some delta neighborhood, then this is a stopping criteria or a convergence criteria. And the second alternative is if your function value that is evaluated at this new point that you get x1, if you are already very close to 0, so that means you almost find the exact root of this problem. So if you are in the epsilon neighborhood for your function's value within this epsilon neighborhood, you can stop the algorithm and you can return this flag to just show that or indicate to the user that the convergence criteria has been satisfied, so that the user knows that the number of iterations was sufficient and your convergence criteria has been satisfied. So this can be used as a sample code for you.